So, hello everyone and welcome back. In this session we will go to the turbulent flow case, which is a bit more interesting, a bit more complicated maybe in terms of flow physics, but to run the simulation is very straightforward, as we will see in a minute. So we will see the 2D impinging jet. So an impinging jet is a very common benchmark in CFD also to validate codes, and it's one of my favorite flows. It's really beautiful. You can see here that you have an inner pipe that's injecting flow towards the bottom of the bottom wall, and then you have all of these beautiful circulations here to the right and the left. It's basically an axisymmetric domain, so we can save a bit of cells, so we simulate only one sector or one cross section of this right hand side or left hand side, and then to visualize it you can use a reflect filter or something that I will show you in ParaView. But as you can see, the flow dynamics are quite complicated in this problem, and it's a highly turbulent flow. But you can also play around and see what would the flow look like if you run it in a laminar flow configuration, and then you increase the Reynolds number step by step to start to see turbulence effects. But yeah, let's go ahead to the terminal and see how we can run this problem. So go now to this. Let's say this is your working directory. Go inside tflows, and then you list, you have tests, sources. I keep repeating this because it's very good to have the structure of the code in your mind so you don't lose track of where you are. But you can also feel free, if you want to use the GUI of your system, you want to navigate through the folders from here, that's fine. But it's a good practice also to know how to use smoothly and fluently the terminal, because it will make the process much more efficient for you. So we go through tests, and we go through, so we choose a RANS case because this impinging jet is inside the RANS directory. So you can see it here, impinging jet to the distant Reynolds number 23,000. So it's a quite turbulent flow case. We can clear here a bit so we can see what's inside. And if you go inside this folder, you will find the case setup and the defined scripts and everything. As we said before, we have two most important files in any case: a control file, which is your input, or the case setup basically has all the control parameters, physics parameters, flow variables, and everything that you need to set up, boundary conditions, and so on. And the second file is the geometry file or the mesh file. In this case, we don't have geometry file. We have the mesh directly from, I think Gmesh was constructed in Gmesh, and you have it in this neutral gambit. So I guess the mesh was constructed by neutral gambit in this format. So we need to unzip it first, and then we start dividing the domain. Because it's a turbulent flow case, maybe it's better for us to run it in parallel, and also we see we see how to run the code in parallel also, and I will show you a few details about that. But before we run the case, we have to go back and make sure that we compile the code in parallel. If we go back here, is sources here? Yeah. So sources, we go to process, and when we go to process, that's the main directory where we want to compile the code. If it's compiled already in serial, then you just need to make clean. So you clean the compiled code, and then we make it, but into MPI-yes. MPI-yes means that we're now compiling the code with message passing interface. So we're preparing the code to run in parallel. And then there's one last thing here that you need to do or pass. Is this argument, directory case. So directory case here takes your compiled code and links it with the test directory, which is the impinging jet. And I will show you in a second why is this important. So we talked about these user mod functions. So user mod functions are actually templates that can execute some functionality to your code while running, and you can add some options through, let's say you want to create a specific inlet profile, or you want to collect some data, statistics for turbulence, stuff like that. And in this case, the user mod functions are important for our case to save some results and define the Nusselt number, to calculate the Nusselt number, because it also has some heat transfer included in this problem. So that's why we're hooking up these user mod functions through the option directory case, and then you put the path to this problem so you can activate those user mod functions inside the case and link them to the compiled code. Takes about 1 minute, 1.5 minutes. Then once you have the code compiled, which is now done, we can go back. Here I'm typing CP, but that's an alias I have in my bash RC. We can make all types of shortcuts that you'd like to have, but if you don't have this one already, then you can use cd space dash like that. Then it brings you back to the previous directory. So now that we're back, we can either construct the problem step by step, or since we done that already, we can use the run scripts. So we can use the run cases, and in order to use that, we can just do sh run case, and then it should run the case for you. It takes this zip file and then extracts it, which is the mesh. Now the first step is converting the mesh to the local format using the tflows convert program. After it converts the mesh is ready now for us. Before it parallelizes the domain or decomposes the domain, it asks you first, do you want to run in serial? Then it doesn't execute the divide program. If you want to run in parallel, then you can pass the argument parallel, and then it divides the domain into 4 domains, and then it starts the solution automatically. You can see here already it started process already, which is the numerical solver is now working already in parallel mode. So it's executing the problem in 4 processors. You can see already all the residuals that I talked about before, UVW, and then you have K epsilon zeta f, because those are the transport equations that you're using in this problem. So if we can add a new tab here, so I can show you a couple of other things while the solution is progressing. We can go to Control-Shift-T to open the new tab for you. And then we can tail the solution like this. And then what I'm doing now is clicking on tab if you don't know this feature already. So you don't have to type the whole output file name, but you can maybe, instead of output results blah blah blah, you can put OU or O and then click on tab on your keyboard. Then it completes the file name for you. So it automatically triggers what's inside the directory and completes the text. Now we're at time step 26. So maybe, I guess it saves every 60 time steps. So maybe we can go ahead and touch save now, so we can see where the solution is now. I'm curious to know what's happening. Paraview, and then let's visualize what's happening. Now we can open, let's say, one of the VTU files. We have now PVTU, and that's important because that's the parallel version of VTU. So when you run in parallel, you're gonna need to look for the PVTU file instead of the VTU, because that's the parallel version that packs up what's inside these sub-directories. You have subdomain 1, 2, 3, 4, because you divided the domain into subdomains. Makes sense. And what we did in tflows is just that to collect the solution inside these subdirectories instead of cluttering the whole directory. So these are just containing the solution of each subdomain inside each of these directories. And what the PVTU does is that it's kind of a wrapper that this wrapper takes what's inside each of the subdomains, puts them together, and then you have the solution of the whole domain. So if you click on this one, it should show you the whole domain. Great. So you can see already I have a beautiful mesh here. It's created by Neutral Gambit, was a tool in ANSYS back in the day. Then you see close to the walls here, you have inflation layers to represent the boundary layer in a good way. Then you have in the bottom wall, the lower wall, we have here also inflation layers to treat the boundary layer properly. And then you have the outlet here again. So you have this, you can kind of expect what the solution would look like. Have an impinging jet here. What happens in the floor is that we have a hot plate here, or a hot bottom floor, and this wall is kind of cooled down by the upstream flow, and then it goes back like this. Then what we're expecting is to see the flow circulation, but also to see the temperature changing a bit here, and it kind of sweeps, or it crawls the temperature drop in this direction. So it's kind of an interesting problem to see, and also to analyze. Let's go back to the control file. Maybe I show you some of the stuff that you can use to analyze what's happening in the flow. So if we close this guy for now, we go to the control file. I will show you what's happening in the processor on the kernel side, but let's see the control file first. I show you a couple of stuff. So I have here, as we mentioned earlier, time step, problem name at the beginning. We have the energy equation activated because we have heat transfer, and we want to know what's happening temperature-wise throughout the domain. We're saving the results every 60 time steps and backing up the solution every 120. And then you can play with these parameters according to your needs, or what's the frequency you like. It's up to you. And here is the backup file. You define here if you have a backup file already that you want to retrieve the solution from. When you have it, you can activate this line uncommented, and then it will retrieve the solution automatically from what you define over here. Time step 400, 5000, and then the meaning of this is that sometimes you need to restart the solution from a specific point, because it's better to when you restart the solution, you're basically starting the solution again, but from a further point in time in the flow. So you're, let's say if the solution is reinitialized by a better value than the initial value, and then it makes the solution also go faster. And then if you want to collect turbulent flow statistics or something like that, then it's definitely the way to go to decontaminate your solution. At the beginning, the solution, we call it contaminated because it's very far from what the fully developed turbulent flow would look like. But anyway, so the control points we talked about before, you can put as much as you want to analyze what's happening with pressure, temperature, velocity field in azimuthal direction, radial direction here. It's cylindrical coordinates here. And then you go to physical models. We talked about this is the physics parameters, or the physical parameters of the fluid. And then you have here the turbulence model. You can switch it on or off according to your needs. In this case, since we know it's turbulent flow already, we can use K epsilon or K epsilon zeta f. Zeta f here is kind of an advanced model a bit, that takes into account the anisotropy of the turbulent boundary layer, but that's an advanced topic. I wouldn't like to dive into it for now, for the relevance of the course. So it's just, you can deal with it as a turbulence model. You can also feel free to use K epsilon or K omega and compare the results for yourself so you can see the differences, but the details of turbulence that would follow in another course. For numerical parameters, you can, if that you want to use the default values, or if you want to tweak something according to your needs, or if you want to see the convergence rate, or want to make a sensitivity study on something, you can always play with these. So we explained all of that before. And the potential initialization, as I said before, sometimes it helps to approach the solution in a faster way a bit instead of starting from scratch. So I guess that's what I wanted to show you in the control file, and now we can see where we are from the solution now. So we fail to see, we're at time step 300, so that's already a good progress. And before we go to ParaView, and then maybe we can give the solution some time to advance more, and then we can have a later step in ParaView. In the meantime, I can show you what's happening in the background. So if you want to see, let's say you lost track of what you're running in the background, because now if you clean this, Control L cleans your terminal, and then you're somewhere, let's say your CD, you go to the root, but you don't know what you're running, where you're running it. And what you do for this is either you use Top, which is a tool that comes with Ubuntu already inherent in the system, and Top gives you, Tops is a tool that shows you all the kernel managed processes or kernel managed jobs, basically all the jobs running on the computer, what the RAM is consumed, or where the RAM of your, where the memory, sorry, of your desktop is used for, what type of processors, or how many number of processors, how many processors you have exploited in what exactly, and what's the PID or the ID of this job is. So as you can see here on the top of this list, you have 4 processes, which is the main solver. That's the name of our program. The solver in TFlow is called process, as you know. We have 4 of them because we're running the problem in parallel on 4 processors. So that's fair enough. And the status here, that's all what you need to know is the status, the name of the processor, the name of the process that consumes this processor. Status is running, it's R, identified by R here. And on the very left, you need to know these numbers, or you don't need to know them, but you need to be aware of what they represent. So each of these represent a job ID. It's a unique number that can give you an information about the ID that if you, let's say if you want to brute force kill it, then you have to use this ID to kill the process, right? There is one more use of these ID numbers, is that if you, let's say you get out of here, Control C, and then you want to know, we are now in a root directory, home, and then the username, right? But we don't know where these processes are running. I mean, we know now because we ran the problem from a specific directory, but let's say we lost track and we're running so many programs and so many codes at the same time, and you want to know where this directory is, so I can go back and kill the process or do some modifications on the solver. So what you do here is to type pwd, and pwd is what shows you the directory or the path that you're on, if you remember from the second or first session, and you add x, pwd x, that will show you, and then you add here on top of that one of these IDs, one of these processors, because all of them are running from the same source or the same directory, so you don't care. Just take one of these and then hit enter, and then all of a sudden it shows you the path of this job or the path of this simulation or process, right? And if you cd to that, you navigate to this, you go back to the initial case where you're running your problem. You can tail here again, and everything is fine. Now, if you remember, if you want to terminate the solution, you can touch exit now, or if you want to save the solution in between 2 time step intervals, you can say touch save now instead of exit now. Then it saves the solution and then it carries on with the simulation. But I'm not sure if we want to exit now, but let's say we want to see something on the fly with ParaView. So instead of writing ParaView again, since we opened it already before, you can put this exclamation mark. I'm trying to give you as much as possible of these tips and tricks that can make you faster a bit with the process. So it's like a text replacement. If you put this exclamation mark, then it executes for you the last command that you passed it to the terminal that has para, which is ParaView, which was in our case ParaView something. There are so many of these commands that we can learn them together step by step. Now if we open ParaView, if you remember, what we need to look for is the PVTU files. So now I'm gonna go ahead actually and select all the list, because maybe we can see the time progression of the flow, right? If we open this, it shows us the domain. We can, let's say, this is the mesh, showed you already the mesh, so we can go to surface again. Then let's say we want to visualize the velocity field, right? The velocity field, we have a profile here at the beginning that is read in the control file. Let's say parabolic profile. And this velocity profile propagates towards the bottom wall, and then it hits the wall to cool down the wall a bit, the hot wall here a bit. So what we want to do, let's say if you want to have a good visualization of your results, we will add one more filter here in this case, because we're running in parallel. That's not in serial anymore. So what you need to do, is to run or to look for a filter that's called clean to grid. And clean to grid is basically cleaning the interfaces between processors. It gives you a clean picture of the whole domain without the nasty interfaces between processors. I'm not sure if you can visualize it here, but in some cases it's clearer than others. Let's say if you don't use the filter and then we're visualizing the domain, let's say use this opacity to visualize. So here it's not very clear, but it shows up when you have maybe but it shows up maybe when you have the results and you have velocity or pressure contours, and then you see these nasty cracks or nasty jumps between two adjacent cells. So it's always safer to use clean to grid when you're doing parallel processors, because then it removes these interfaces and it collects the whole domain into one chunk. So that's the first filter we need to use, and then the second one is let's say cell data to point data. Cell data to point data to interpolate the results from the cell center to the nodes. Then we can have a smoother look of our velocity field. So if we that's y plus, this is the velocity field, and if we hit play, then you can see that the solution progresses very quickly. It goes here and it hits the wall, and then once it hits the wall, it can kind of reflects with some eddies here. You can see it's beautiful dynamics that's happening inside this domain. And you can also go to temperature, and maybe temperature will give you a good representation of what's happening. Not sure if you can see it here, because this one is clearer a bit. You can see already that here is a bit hotter on the temperature scale. This part of the wall is a bit hotter than this, because here the flow has hit the wall already and started to cool down. If you can see it properly, maybe you can change the color palette maybe into, I don't know, cool to warm, but a bit of saturated level. And yeah, maybe here is a bit nicer to see. But you can always wait on the solution a bit more, and then more advection of the flow can give you a better idea about the bottom wall. But yeah, you can see already here. So I guess that this is just that we didn't adjust the range of the data. You can see it's very smooth. If we don't use this filter as we showed before, it's a bit, let's say it's a bit pixelized, and that's actually the more accurate representation about the flow, because it's not interpolated. But you want to use it maybe for some visuals or some technical report. But if you want to look into some deeper details between cells, or you're debugging something, maybe it's a good idea to look within these with these values that are uninterpolated values of the grid. If you want to see a specific value, I guess was this filter here, this tool, that you can go to any cell and hover. If you hover over it, then you will find all the details or all the parameters that are spotted or that are reported from the VTU file on the screen here, and you can take all the values that you need. If you want to see something on the interface or the boundary condition, or something that is a patch surface or something that you have some interest in, you can always visualize it through this. One last filter here that I want to show you, so you can have one more tool to work with, is the reflect filter. And this reflect filter, basically, if you don't have it here because I just used it, you can search for it here, and once you find it, you can click on reflect. And then if you reflect, you can obviously reflect, it's like a mirroring filter over an X plane or Y or Z. And if you reflect here over X, then you have some kind of a mirrored picture of the domain around the Z axis, right? So it's mirrored in X direction around the Z axis. And if you want to visualize the domain again, you can kind of see that the flow was intended to be. So you can see already now, if you visualize the velocity field, that the flow is already a cylindrical flow. It's an axisymmetric flow, but we just took this part of the domain to reduce the cell count. But you can always, instead of, it's kind of a more representable picture about the flow, and then it's of course completed here. So this cylinder, you have now more of a 3D effect of what's happening, if you like, but that's just an option that I wanted to show you. But it's basically just copying what happens on the right domain and mirroring it across the axis. So that's it from this side on ParaView, and maybe I can show you the animations that I prepared already, but here it takes you a couple of minutes, maybe it takes half an hour or something. I'm not sure if you have here 600 time steps and 4 processors. Depends also what type of processor you have. Maybe you have a more powerful processor in your case, or less powerful, so it depends. These times you don't have to take them so seriously because it's very case specific on each computer. Just give it a bit of time. Maybe if you need, if you have more processors, or if you're using a cluster, you can always scale up and use more processors to fasten up the process a bit. Here we are on 23 minutes, but we can already terminate the solution. And like that, we touch exit now, because now you have the idea already. Maybe I can show you the animations that I saved already before this session. And I put here impinging. You can see already kind of, maybe you can rotate this GIF to have nice pictures, but it's you get the idea already. So this is here, it's negative Z direction. It's kind of hitting this wall, or if you rotate it, it's hitting the bottom wall. Then you have all of these circulations and beautiful eddies coming from the viscous effects of the flow. So one last thing maybe that I want to show you before we end this session is how to use the backup files. So let's say we have here a couple of backup files already. Let's say we want to use this last one at time step 703. What you need to do is, let's just make sure first we don't have anything running anymore. Yeah, by the way, you also have top, and you have also htop, which is maybe more beautiful too, or a clearer representation, gives you more information about the memory, swap memory. And you have also all of the processes here and the status, all of the cores or your computer cores, and what's happening. You have the PID and the user and the status, as I showed you before, and how much percentage-wise it consumes from your CPU. So those are the tools. Top and htop. Top comes automatically with your Ubuntu system or your system, and htop you need to install with sudo apt-get install htop. It's an open source tool also as well. What we need to do here is just that I show you the backup file, how to use the backup file. So let's say if you want to use this one in the control, we go to control file and you copy paste this one, you uncomment this solution, sorry, and then let's go to the first line again here. Oh, yes, and let's delete this guy and put our name 703. Click on escape, right, quit, and yes, we're ready. In order to restart the solution now, maybe you need to modify in the bash script, which is this one, if you want to modify in this one, but maybe it's an easier option here is just to run it manually yourself by mpi run. So this is mpi run -np and the 4 processors that we're using, and put the the program name, which is process, the tflow's program name that we need for this, and then you flush it maybe on you put, instead of this file that we have already, maybe you say output 2 or the log file 2, and don't forget the and sign in the end. So this will restart the solution, but from this guy. Instead of the restarting the solution from scratch, it will take from this one as an initial input. If you hit on enter, then you can track what's happening with a tail again, and then you can see already that the solution is progressing past this point. And if you want to make sure again, you stop and you have these 4 processes, and then maybe more elegantly, if you want to kill, let's say if you have a very emergent case and you want to brute force killing the case, then instead of using touch, but I don't recommend this one, touch exit now, we used to use this one, which is the elegant way, the non-elegant way to go about it. And let's say you need, or you're forced to use it for some specific case, then you can use pkill and you write the program name, which is process. Or one more non-elegant way, but I don't recommend either of them, is to use top. And when you go to top, then you choose one of these names, one of these PIDs, and then you can say either pkill or kill -9. Then you put the ID name. Then it kind of kills the process, but in a very aggressive way. You can see already that it's not working anymore, but it's a non-elegant way. I don't like to use it really, and I like to end the program in peace. But just that you have all the tools in your mind while working, just in case that maybe your system freezes or something. You need also to know these tools. I hope you enjoyed this session. Please make sure that you take enough time to run it yourself and maybe play around a bit with the control file and see where you get with this case. If you have any questions, don't hesitate to drop me an email. And yeah, thank you very much for watching, and see you next time.